Now what does that mean if that thing with the pole, the singularity, it's still a function of omega. So for some value of omega, I'm going to have a singularity. So for some value of omega, several ones, I'm going to have a singular matrix here. What is the singular matrix? I mean, in the diagonal case, I'm going to get a 0 here. So I have a 0 in the diagonal element. And that means I can't calculate the inverse of the matrix any longer. So if you have a singular matrix, you can't calculate the inverse of that matrix. There's actually another mathematical problem where you have singular matrices. Where you have the case of a singular matrix, and you're actually looking for, it's a condition. That's, if I have a matrix A, here vector x of unknowns, and that's equal to 0. Homogeneous linear equations. For homogeneous linear equations, in order to have the non-trivial solution, I mean the trivial solution would be x, the vector x, is equal to this. I just multiply with the inverse of the matrix on both sides, and I get x is equal times the inverse of the matrix A times the right-hand side, which is 0. But that's 0. So if I can calculate, this is still 0, so my solution is a 0 vector. That's what is called the trivial solution to a homogeneous set of linear equations, which we are not interested in. So we are, in order to get a non-trivial solution, we should be not able to do this here. So a homogeneous set of linear equations has a non-trivial solution if you can't calculate the inverse. So if the matrix is singular. And then if you ever have done this with secular equations, calculate molecular orbital coefficients by solving secular equations, and you got the secular determinant, and you found the orbital energies from the secular determinant. You do that because you're trying to find for which values of the energy does the matrix become singular. We have the same here. We want to have this matrix to become singular, because then we know that the omega corresponds to an excitation energy. So we just can write that up in the same way and say, okay, this matrix to be singular means that the corresponding set of linear equations has a solution. So I can write up h bar omega times the S matrix minus this E matrix times some vector x, some unknown vector x equal to 0. When this set of linear equations has a solution, then I know that this matrix is singular. When this matrix is singular, I know that the omega corresponds to an excitation energy. Now that I can rewrite. I can write that as E x is equals to h bar omega s times x. Just split that matrix up. I mean, it's not the inverse any longer. Split it up right like this. And this is just, well, it would be an eigenvalue problem if that s wouldn't be there. With that s, we call that a generalized eigenvalue problem. So, and the eigenvalues are the frequencies omega for which this matrix is singular, which means for which our response function has a pole, which means they are excitation energies. So when we nowadays calculate excitation energies, we don't do what we could. We don't do just tune through all the frequencies and say, oops, here was a singularity, that must be an excitation energy. But we actually go directly after them by solving this eigenvalue problem. And it's a bit funny, sort of, if you look at the development of science, because there were times where you discussed doing that by really finding the poles, by tuning through them, and then you can do it much easier this way. In the meantime, there are some people went back to that. Now they go back and just calculating the response function for different frequency and plotting them, and then getting the spectrum directly. There's a small change in it because the omega are extended by some damping. You need some damping in order to get rid of the singularities and just get the tops. But what you're going to do today, on Thursday is the program solves this eigenvalue problem and gets the excitation energies in this way.